Oh, okay. It's recording. Very good. So, yeah, welcome from me also to everyone at this summer school. I hope you're enjoying it and you're learning stuff and you're meeting other people. So, I'm going to give 4 lectures, and my title, the title I was given was Mathematical Concepts, which could mean a lot of things. So, I should just, in the beginning, maybe make more precise what I'm actually going to talk about. So, I will mainly talk about Feynman integrals and mathematical aspects of Feynman integrals. And what I'm going to talk about is Schwinger parameters. So that's a particular way to write down Feynman integrals. Can you read this?
Yes, perfectly.
Awesome. So yes, I want to talk a bit about Schwinger parametric representation. Then I'll spend quite some time on analytic regularization. So this is also, you know, this as the epsilon expansion. So this is how do you define it? How do you compute it? What are the singularities? What are the residues? These kind of things. Then I'll talk about, that's probably going to be in lecture 3, about Landau varieties. So this is also about singularities, but this is about singularities in a different set of parameters. This is in masses and momenta. And finally, hopefully I have some time to talk about monodromy. So in each of these, there are some mathematical concepts going on, you might argue. Obviously, there's many other mathy things that I'm not going to talk about in the lecture, but we have some discussion sessions next week, right? So if there's anything of a mathematical flavor in the other lectures coming up, I don't know, like Hopf algebras of iterated integrals or motivic coactions, cohomology of varieties and things like that, then I'm happy to discuss this in the sessions next week. But this is the plan for these lectures that that we're recording now. Okay. So what am I talking about? So I want to think of scalar L loop Feynman integral families. So what is this? Well, it's a function, and it depends on a bunch of parameters. So there is a parameter d, which is the dimension. So d is the dimension. And the n's are called indices. And there's another parameter, or bunch of parameters rather, which I denote by z. So this is kinematics data. So this is masses or scalar products of momenta of external particles, things like that. So we want to look at functions of these types of variables, and somehow a very general class that is sufficient for applications in perturbative calculations, something like this. So L is what's called the loop number. So there's a certain number of integrations over what is called the loop momentum. I denote the loop momenta by L. So there's loop momenta L1 up to L capital L. So capital L is the loop number, little l is the loop momentum. There is some convention here, some powers of pi and the imaginary constant. So it's some integral over some momenta in Minkowski space of d dimensions. And what you're integrating is a bunch of quadratic forms. So actually I already messed up, but anyway. So you have a certain number of quadratic forms. I will denote these by q. And they are raised to certain powers, which are these n's. And I should have also written the dimension here in blue. So what I want to stress here is that these variables enter in different places in this integral. So there's a dimension, and the indices, they show up as the dimension of the integration domain and in the exponents. And the masses and momenta, they go into these quadratic forms. So these are quadratic expressions in these momenta, in the loop momenta, in the external momenta, and also in the masses. And essentially, you can choose whatever you want and study these integrals. And that's what we want to look at for a bit. So this is a momentum space representation, and I'm sure many of you have seen examples of this. I'll give an example in a second. But the first thing I want to do with this is to introduce what's called the Schwinger parameters to transform this interval. So what do you do here? Well, let's first recall what is the gamma function. Maybe I'll move this up a little bit. What is the gamma function? So gamma of n is defined as an integral from 0 to infinity x to the n minus 1 e to the minus x dx. And if you divide by gamma of n, you get a representation of 1. And then you can change variables and scale x by one of these quadratic forms, say. So it's a very easy exercise to deduce from this that if you have something like 1 over q to the n, you can write this as 1 over gamma n times the integral 0 to infinity x to the n minus 1 e to the minus xq dx. Okay, so with this integral representation, we can replace all of these 1 over q to the n's in the integral in terms of integrals over new variables, these x's, which are the Schwinger parameters. Right, so these are the Schwinger parameters. So we introduce new variables, and they exponentiate all of these quadratic forms. So in particular, then we have the product of all these exponentials, and you can combine them. And what happens then is you get a combined quadratic form. So combined quadrics in the exponent. Oops. So what happens there? So we had n exponents, whatever capital N is, doesn't really matter. For every of these quadratic denominators, we have introduced a variable xe. And now this is, as I said, a quadratic form, so you can decompose it into its quadratic, linear, and constant part. So I'll write some ij from 1 to L, and then we have some product of two loop momenta, say. And aij, I just call the coefficients of these quadratic terms. Then there's linear terms. So some linear combination of the loop momenta. And then there can also be a constant term, whatever that is, C. And now whenever you have this quadratic expression, you can, of course, complete the square. So you can shift the L's a little bit. And then you get a new integral, a new representation for the same expression. And I'll define these L primes in a second. But what you want is to keep the quadratic part, but to cancel the linear part. So you somehow want to write just a constant here. So the point is that this is independent of the loop momenta. And how do you do this? By completing the square. Completing the square. So in this case, you can work it out. I mean, these shifted loop momenta, what you do is you have to subtract a certain multiple of these constants, of the coefficients in the linear part to cancel the linear part. And actually what you need is the inverse matrix, A inverse. And then this delta turns out to be C plus the sum over ij. And then you again have the inverse matrix. And now you have products of these B's. Now, this is again a simple transformation. You can check. And now maybe let's do an example to make this a bit more concrete. So okay, so example. So let's look at this graph here. So now I'm taking an integral family that comes from a graph. That's what you do most of the time. So let's say we have just one external momentum flowing through the graph, and it has 5 edges and 2 loops, and let me route the loop momenta in some form. So we have 2 loop momenta, and you have to ensure that at every vertex you have momentum conservation. So this is just one possibility to write down such a momentum routing. I give the edges numbers. So let me label them 1, 2, 3, 4. And the middle one I call edge 5. And now what kind of denominators do I choose? Well, in standard scalar field theory, what you would do is you would set these denominators to be the inverse propagators. So you would say this is the mass squared minus the momentum flowing through the edge squared. Maybe if you want to be very precise, you have a minus I epsilon. I have conventions that are tailored to Euclidean integrals. So if you don't like the signs, you can change the signs everywhere. It doesn't matter. But so let's take these propagators. So what do we get? Well, this combined quadric, right? It's x1 times the first. And what is the first? Well, it has a mass, and it has the momentum L1 flowing through it, right? And then we have the second, which might also have a mass, minus L2. Then you have the third. Now this has also a mass. Now the momentum here is L2 minus P. Then we have the fourth propagator. And finally, there's a fifth, M5 squared minus L1 minus L2 squared. Right, so this is the exponent after the Schwinger variables were introduced, the linear combination of all of these quadratic terms. And now we can collect these terms. So let's look at the quadratic terms. So let me write it in a kind of matrix expression. So let me write the quadratic terms like this. So what I mean here is that in the top left corner of this matrix, there's a quadratic terms L1 squared. So where do you have an L1 squared or a minus L1 squared? You have it from here, from the fourth and from the fifth, right? So there's an x1 plus x4 plus x5. In the bottom right, you have the L2 squareds. Those come from propagator 2. You have it in 3, and you have it in 5. And then off diagonal, you have they have a half of the cross terms L1 dot L2, so you can read these off. So there is actually it only comes from the x5 here, right? This is the only term that has these mixtures of L1 and L2. And it comes with a minus sign, so you have a minus x5 minus x5. So this is all the quadratic terms, and that here is the matrix A. Then you have linear terms. So let me write these also in a kind of matrix product notation. So this turns out to be this combination. So this is B, right? Where do you get an L1 dot P? Well, you only get it from x4, right? This way you have a L dot P, L1 dot P with an x4, and the third one gives you an L2 dot P. So these are the linear terms. And now for the constant terms, well, you get constant terms with P squared from 3 and 4. So there's a minus P squared times x3 plus x4. These are constant terms. But then you also have constant terms from the masses, right? These terms are constant with respect to the momenta. So you also have a term. All the masses, right? So the masses always come with their corresponding Schwinger parameters. And this is C. Okay, so this is just an example of this completing the square. And now we've done that. So you see A, B, and C, they depend on these variables, x, right? They're all linear. A, B, and C, all the entries are linear in the x's. And it turns out for the integral representation, you don't actually need all the information of these matrices, but only certain combinations of those. So the standard definitions is to define two polynomials. So the first is called the U polynomial, or the first semantic polynomial, and that's just the determinant of the A matrix. And as it's clear from this example, right, this is a polynomial in the x's, and it has integer coefficients. And the second thing you define is another polynomial, which is called f, and this is just u times delta, right? Where delta you get from completing the square. And you can express it in terms of A inverse B and C. Now this is also a polynomial in these variables, but it also depends on the masses and momenta, right? So let me write Z there. So this is just a notation to remind you that these depend on the masses and the momenta. So in the example that we did of this graph, right? So we have this U is the determinant of this matrix that we had above. I'm just copying it here. And now you can work this out. And obviously there is the product of the diagonal terms. But actually when you look at it, right, when you take the product of the diagonal terms as an x5 squared, the x5 squared gets canceled with the off diagonal terms. So actually what's left over is only linear terms in x5. So this would be this U polynomial in this case. And one observation here is, so actually this is linear in each variable individually. That's sometimes quite useful to know. Another thing to note is that actually you see it's a homogeneous polynomial. This is obvious, right? It's a 2 by 2 matrix. Every entry is homogeneous linear in the x's, so the whole thing is quadratic. And that's a completely general observation. So this U polynomial is homogeneous. Homogeneous of degree equal to the loop number L. And the other polynomial is homogeneous in the x's of degree L plus 1. So I'm not working this out. This is an exercise you can do. Maybe I put it on the exercise sheet to work out what f is in this case. But anyway, so the upshot is that all the information of these integral families is encoded in the U and F polynomials that we defined. And how do we wrap this up? So now notice, now that we exponentiated everything, the integral over the loop momenta, right? So we had the product over all of these loops of the integral over the corresponding loop momenta. Now we can shift this, so we can write L primes here everywhere. And then the only dependence after completing the square is in the exponent, right? So we had Li prime dot Lj prime Aij, right? There's other stuff in the integral, the integrals over the Schwinger parameters and these gamma functions and so on. But this is the only part that depends on the loop momenta. And so this is now a Gaussian integral. So that means you can carry it out very easily and express the result in terms of the determinant of A. So this, if you haven't done this, is also a good exercise to just write this integral in terms of the determinant of A. So what you do is you go to an eigenbasis and use the eigenvalues of A. So what is the end result of all this? So when the dust settles, we get this representation of the integral. Let me use my funny color coding again. So for each of these denominators, we had introduced a Schwinger parameter, right? So we have these integrals 0 to infinity x to the n minus 1 dx over gamma. But all the loop momentum integrations are now done, and what's left over is an exponential. I always forget my color coding, I'm sorry. This should be a blue N. Maybe a plus I epsilon if you want to be very precise. And then we have u to the d over 2. So this is what's called the Schwinger parametric integral representation for such an integral family. And what has happened now, one of the many things that happened is that, first of all, the integration now is an integration over an n-dimensional space. Previously, we had to integrate over d-dimensional Minkowski space. Now, whatever the dimension is, we are always integrating over one variable for each denominator, right? So the dimension of this integral does not depend on the space-time dimension in momentum space. Instead, the dimension only comes in here in the exponent of the u polynomial. And what I mean by this red notation is that the only thing in all of this that depends on the masses and momenta is this polynomial f in the exponent. In practice, it is convenient to use some variations of this formula. So there's what's called the Lie Pomeransky form. So what do you do here? It's the same integral written in a different way. So what you get here is some prefactor of gamma functions. And I will explain what this omega is in a second. Then you have the same product, the same integral measure that you had earlier. But now the integrand is replaced by u plus f to the minus d over 2. Yeah. So this is also a good exercise. It's a very simple proof to show that these two are equivalent. I mean, for several reasons, it is nicer sometimes nicer to replace the exponential by such a polynomial here. Particularly in algebraic geometry, this is convenient, but also for other things I will talk about a bit later in the lectures. And then so in here, what is this omega? So this omega is the sum of all these indices minus the loop number times half the dimension. So this is the superficial or the power counting degree of convergence. And I will talk about that later in the next lecture. So this is just a certain number, a linear combination of the n's and the dimension. And then there's also a projective form. So this is yet another equivalent way to write down the integral. But it's neat because it has one integration less. So it turns out that you can always do one of these integrations in closed form. So what you do is you pick a function that maps all the Schwinger parameters to some positive number. And that is homogeneous of degree 1. Right, so that means h of lambda x is lambda h of x. So if you choose any such function, you can always do one integration again, and you can write the integral family as follows. Or you have a different prefactor. Now this superficial degree of convergence comes in the gamma function in the prefactor. Then again, you have the same product of these integrals. But now you have a delta function in the integrand. So actually, it's one integration less. And this delta function is exactly 1 minus hx. So essentially, you can impose an arbitrary constraint, right? Because h is arbitrary up to the constraint that it's homogeneous. And then you have and the u polynomial to the power d over 2 minus omega, and you have the f polynomial to the power omega. Okay, so this is 3 different ways to write down Schwinger parametric forms for the Feynman integrals. And in the rest of this in the next lecture, I want to talk about mainly the dependence on these variables, the d's and d and n. And in the last 2 lectures, I will talk about the dependence on z. Right, so the questions are in particular, when is this integral well defined? What are its poles? What are its residues? Epsilon expansion, and these kind of questions. So this is what I'm going to talk about for now. Okay, I don't hear any questions, so I'll just continue. Before I go too much into these analytic continuation questions, I just want to sketch briefly what these polynomials are. So I defined them as determinants, and through this completing the square procedure. And that's what they are, and you can always use these definitions. But in many cases, it is actually sufficient, and essentially in all cases, it is in the end of the day, it is sufficient to consider not arbitrary integral families, but only those where the quadratic forms are the inverse propagators from a graph. So let's assume that we have all of these quadratic forms of this form, me squared minus ke squared, where ke is the momentum flowing through the edge E. So if we have a graph and the momentum flow of the graph, and we define our denominators in this way, so this is what I mean by is given by a graph. Then you can give formulas for these polynomials, which are useful in several applications. So this u polynomial you can write as the sum over all spanning trees. So you sum over all t's that are spanning trees, and you take the product of the edges not in t, xe. So what does this mean? What is a spanning tree? Well, the first thing is that it has to be spanning and connected. So let me give 2 examples. So I look at the previous example of this 2-loop graph, and let me say I only take this this edge here. Then the problem is it's not spanning because it doesn't connect to the other 2 vertices. But also if you take 2 edges, so you take this edge and this edge in the bottom right, and you take this as your set t, and the problem is it's not connected because you cannot go from this part of the tree to this part of the tree. So actually it's a forest and not a tree. So these are excluded. So these are not connected or spanning. So those are no good. Another thing that's no good is this thing. So let's suppose you take all of these edges here. So you only leave out this one edge on the top right, but you take every other edge and you call this t. Then it connects everything. So right, you can go from every vertex to every vertex within there. But the problem is it's not a tree because somehow its root connects to a branch. So this is not a tree because it has a loop. Right, so you can go through a loop here, and that's not allowed. So everything else is a tree. So an example would be if you take, for example, these 3 edges. All right, so this is a tree. This is a tree. And let me remind you what the edge labels were. So I call these 1, 2, 3, 4, 5. So this would contribute a term to the U polynomial. They take the product of the edges not in the tree. So this would give you an x2, x4 summand in the U polynomial. And then, of course, there's many other trees. Right? An exercise is, of course, to enumerate all the trees and compare with the determinant of A calculation that we did earlier. Now, this is the statement about U. You can also write a formula for F. So F is the sum over spanning two forests. I'll explain in a second what that is. Now, for every two forests, there is a momentum flowing through this two forests. So you take this. So this is where the kinematics comes in. Then you have a product over all the edges not in F. And then you have another contribution. You just take U times the sum over all the mass terms. And just to give an example of what the two forest is, well, that's a direct partition into two trees, the two disjoint trees that overall is spanning. So to give an example again, how would this look like? So for example, if you take only two edges this time. So previously this set was not allowed. This was one of the excluded sets because it's not connected. If I only take these two edges. But actually, so this is two trees, right? So now we are allowed to be disconnected. We want to have exactly two components, and each component is a tree, so that's good. So again, this was edge 1, 2, 3, 4, 5. And now because we have two components, there corresponds a cut of the graph. Right? There's one component, another component, and then there's a momentum flowing through this cut, right? And this is this momentum PF. So this gives a contribution to the F polynomial, which is minus p squared, because in this case, the entire external momentum flows through this cut, right? And the edges that we have to lead is x2, x4, x5. This is one summand to the F polynomial. There's many more. Let me just give one more example to clarify what this two forest notation means. There's also kind of degenerate cases where one of the trees has only a single vertex. So this would in principle also be a two forest, right? It has one tree here and a very poor tree with just a trunk on the other side. So it cuts the graph into two pieces. But in this case, there's actually no momentum flowing through this cut, right? Because there's no external momentum in this component T2. So this would actually give 0. X3, X4, X5. Now that's not always the case. I mean, you can also have these degenerate trees with non-zero contributions. So if you take this one. So again, it's just a single vertex on one of these components. But in this case, so here, this side, the cut is here, but in this case, indeed, you do cut the flow of the momentum, right? You have the momentum p squared in one component and minus p squared in the other. So this does actually contribute. It's 2x3, x4. Okay, and so on. So this is just an illustration of how this looks like. And this can be quite useful in small examples if you want to write down what these are, but this is also useful to prove some of the theorems I'm going to mention a bit later. So maybe keep that in mind. Now, at the end of the first lecture, I want to start talking about the singularities and divergences. So the questions are, when do these integrals converge? Questions. When does an integral converge? And where are its singularities? I mean, in some sense, this is the same question, really. But maybe more importantly, what type are the singularities? But singularities can take many shapes. You can have poles, you can have logarithms, you can have essential singularities. So you want to get an understanding of what this looks like. Especially because in the end, maybe you want to use the dimension as a regulator. So you want to talk about Laurent expansions in D or in epsilon. So this is why I'm going to explain this. So in order to get a feeling for this, let's look at a simple example. So it's always the same example. No, it's not always the same example, right? So now let me take this even simpler example, which is just two propagators. Again, external momentum P, L, and L minus P, momentum flowing through. And then let me write down this integral. Again, in momentum space, just to remind you. So this is an integral over a single loop momentum, so I'll get rid of the subscript. And then we have minus L squared minus I epsilon. And we have minus L minus P squared minus I epsilon for the second one. So here I'm using the massless case. So I'm setting the masses to 0 just to make it simpler. And then in the parametric representation that I explained earlier, so we get a prefactor gamma of omega. And then from the integration, we have these gamma n1, gamma n2. What is omega in this case, by the way? This is a single loop, this graph. So omega is just n1 plus n2 minus d over 2. So that's the prefactor. And then we have a double integral. But we also have this projective representation. So let me use the projective representation with h of x being x2. Right? So I would have a two-dimensional integral, but I have used this delta function to set x2 to 1. And then only a single integral remains from 0 to infinity. And if you work it out, there is x1 to the n1 minus omega minus 1 over x1 plus 1 to the d over 2 minus omega. And there's a minus p squared to the omega and a dx1. So I suggest you do this as a little exercise. So the point here is that u turns out to be x1 plus x2, and f turns out to be minus p squared x1 times x2. And if you use these and set x2 to 1, you get this expression. So it's just a one-fold integral. So indeed, it turns out you can do this explicitly. But what I want to focus on is whether this actually makes sense, this integral, right? You see, when x1 gets very small, right, the integrand is determined by this monomial here, this power of x. And if the exponent is too small, you will get a divergence at 0. Similarly, if x1 gets very large and the exponent is too big compared to the exponent in the denominator, then again you will get a divergence. So actually, when you think about it for a little bit, you will see this integral converges only when, well, first of all, you need the real part of n1 minus omega, which is not the same as the real part of d over 2 minus n2. Right, so you have to have this positive. Right, so this comes from when you think about what happens when x1 goes to 0. When you look at the power counting when x1 becomes large, you get a second condition. You also want that, you also need that real part of n1 minus d2 is less than 0. Yeah. So when you get very large, the omegas cancel, right? Asymptotically, the x1 cancels this, so you're only left with the n1 relative to the d over 2. So these are the two constraints. So this comes from x1 going to infinity. Okay, so we know that this integral converges only in this region. So probably, you know, it looks like there might be poles when we're at the boundary of this region, and indeed there are. But you can also check from the integral that indeed you get singularities when you're there. But then the question is, what happens beyond those singularities? Right, and here we are lucky because we can write down a closed form for this integral. So it turns out you can write it like this. So there's a certain power of the momentum that's just given by the power counting mass dimension. And then you have a bunch of gamma functions. So there's a gamma of d over 2 minus n1, gamma of d over 2 minus n2. And then we have the gamma of omega. Let me write it like this. And then there is a couple more gamma functions, n1 in the denominator. But notice the denominator doesn't matter for divergences, right? The gamma function in the denominator only brings in some zeros. The poles only come from gamma functions in the numerator. So what are the observations when you look at this? So you should notice, so this is a meromorphic continuation of the function, right, to all of C3. Right, so you can take the dimension and the indices to be complex numbers, any complex numbers, and then these gamma functions make sense. So this is a meromorphic function. So even though the integral doesn't converge for x1 smaller than 0, or sorry, for n1 bigger than d over 2, for example, the exact result actually shows us that we can continue the function there, and that it's meromorphic. So in particular, this means it is single valued. There is no monodromy in these variables. And the second observation is we have simple poles. So the singularities are very simple. So they're just poles, and they're only poles of first order, right? The gamma functions only have poles of first order. So there's no higher order poles. And where are these poles? Well, you know where the poles of the gamma function are. If you don't know, I'll recall this in a second on the next page. But the upshot is that the divergences are whenever any of these three arguments in the gamma functions is a non-positive integer. So if it's 0 or -1 or -2, this is where the poles are. So we learned that a Feynman integral, even though it converges only in a small domain, actually it extends to a meromorphic function, and it has only simple poles. And I want to explain a little bit how this goes. But maybe to finish the first lecture, let me just try to draw this in a diagram, this observation here. So let me draw this convergence region in a diagram. So let me say, okay, we have n1 and n2. And then somewhere, whatever the value of d is, right, we have the point d over 2. And then somewhere there is d over 2 plus 1 and d over 2 plus 2. I hope that you can read this. Maybe you need to zoom in. So then we know quite a lot about the poles. You know everything about the poles, right? So first of all, there's a singularity when n1 plus n2 is d over 2, right? So on this line, you have a pole of the Feynman integral. Also, when it's -1, maybe that's about here or here, right? So these poles, they continue forever. They start somewhere, and then these lines just get shifted, and you always get a new pole. So this is the pole when n1 plus n2 is equal to d half. This is the pole at n1 plus n2 equals d half minus 1, and so on. This is the first family of poles. Then we also had poles at n1 equal d over 2. So that's a pole on this line. And we had a pole at d over 2 plus 1 and d over 2 plus 2 and so on, right? So there's another family of poles that are these vertical lines, and then you also have poles on these horizontal lines. And that's it. Okay. So these also continue. So these are the poles. And then there's this tiny region in here, this little triangle. Right, so this is the thing that's beyond all the poles, right? This is bounded by the first pole of each of these three types. So in here, the integral is convergent. So this is the domain of convergence. Of the integral. Now, of course, in this simple example, right, we know the exact solution and you can just read it off. So what's the point? So the point is to try to explain how this generalizes to arbitrary Feynman integrals. So to see that every Feynman integral has a meromorphic continuation and to understand where its poles are and how the epsilon expansions around these poles looks like. So this is what I'm going to address in the next lecture. But maybe this is a good point to take a little break, maybe. Break, okay? Should I take a break? Good. Okay, so I take a break and I'll be back in 5 minutes.